On July 29, 1958, the Space Act created NASA, and buried in its founding charter was language broad enough to send engineers not only toward orbit, but to the bottom of the ocean. Early appropriations confirm it. Line items from 1959 and 1960 routed agency funds into pressure hulls, underwater testing, deep sea survivability, the secret ocean routes of the space program hidden in the budget trail. Then those programs vanished. The money pivoted to the moon. What no one asked was what got left behind, and why certain naval records from that era still carry entries logged as unexplained. When the Soviet Union launched Sputnik in October 1957, the United States scrambled to unify its fragmented aeronautical programs under a single civilian authority. The legislative solution was the National Aeronautics and Space Act of 1958. This founding charter did not limit the new agency's scientific pursuit solely to orbit or outer space. Instead, the statutory language authorized NASA to conduct research into problems of flight within and outside the Earth's atmosphere. While the word outside pointed toward spaceflight, the word within legally permitted the agency to investigate extreme physical environments on Earth. This open-ended directive allowed early administrators to look downward. The physiological limits of human survival and the structural integrity of pressurized cabins in high-altitude flight shared direct, quantifiable parallels with the crushing environment of the deep ocean. Examining this early crossover is a matter of administrative and engineering history, not speculative myth. The archival record reveals a highly logical partnership between early aerospace planners and marine researchers. Understanding how NASA's priorities eventually narrowed toward the moon requires tracing how its original mandate permitted this initial descent into the sea. In its first fiscal cycles, the newly formed space agency operated as a broad-spectrum scientific institution rather than a single-mission moon project. The financial records from fiscal years 1959 and 1960 reveal how this mandate was funded. Congress authorized over $533 million for this initial two-year period, with actual appropriations rising from $369 million in 1959 to $485 million in 1960. Within these massive ledger sheets, there was no separate, isolated line item labeled for ocean exploration. Instead, the funding was distributed across wide research and development envelopes. Early planners designed these programs to investigate fundamental physics, material science, and survival limits in any extreme medium. The ocean was not an afterthought. It was built into the very architecture of these early research models. The budget trail demonstrates that before a lunar landing dominated the national policy, NASA possessed the resources and the institutional interest to study extreme environments wherever they existed, including the crushing environments of the Earth's own oceans. The administrative structure behind these early efforts resided within the Office of Advanced Research and Technology, known as OART. Created at NASA's inception, this headquarters division managed cross-cutting research in high-pressure systems, life support logistics, and material science. Rather than isolating oceanic work as a standalone program, OART served as an internal mechanism for technical crossovers, applying subaquatic research directly to high-altitude aeronautics. Outside the civilian space agency, a parallel engineering culture existed within the United States Navy and the Office of Naval Research. The Navy's deep submersible designs, pressure hull testing facilities, and underwater acoustics programs provided a highly compatible external counterpart to NASA's research aims. This institutional alignment enabled both agencies to share test environments, physical data sets, and engineering standards without a dedicated, separate oceanographic division. The connection between sea and space operated through these shared networks and administrative pathways, forming a practical foundation for extreme environment research before national priorities redirected resources toward the moon. At depths of several thousand feet, water exerts thousands of pounds of force on every square inch of a submerged structure. This hydrostatic force is the primary engineering barrier of the abyss. In the early 1960s, marine researchers addressed this challenge by testing specialized pressure vessels, including diving bells, underwater habitats, and bathyscaphes. The bathyscaphe Trieste utilized a spherical steel hull designed to distribute external loads uniformly across its surface, preventing structural collapse under immense weight. For aerospace planners, these vessels served as real-world laboratories for studying containment under stress. Designing a cabin to hold 1 atmosphere of internal pressure against the vacuum of space relied on the same physical logic as building a hull to keep water out. NASA researchers studied the welding techniques, metal seal behaviors, and structural tolerances of these naval hulls to observe how materials react to physical deformation. This analysis provided mathematical models for preventing microscopic leaks and structural failure, converting underwater engineering lessons into a basis for human survivability. Operating inside a sealed capsule required more than structural survival. It demanded active environmental management. During the 1963 to 1965 period, aerospace planners studied naval methods for carbon dioxide scrubbing and humidity control to refine spacecraft life support. Human training also moved underwater. In 1964, NASA's Langley Research Center contracted Environmental Research Associates to simulate altered gravity conditions using water-filled tanks, adapting Navy diving procedures. Simultaneously, undersea operations yielded mathematical tools for data transmission. At the Navy's Atlantic Undersea Test and Evaluation Center, engineers developed hydrophone timing arrays and signal filtering algorithms to isolate acoustic pings from background noise. These timing disciplines provided the template for synchronizing spacecraft telemetry streams. The hydraulic actuator, control loops, and remote operator feedback systems used in early naval submersibles offered direct operational logic for developing robotic manipulators. This moved the focus from survival to active telemetry and system control. On January 6, 1960, the United States Navy issued Operation Plan Comme des Flottes 4, number 160. This directive established the operational framework for Project Mercury recovery missions, defining splashdown zones, helicopter retrieval protocols, and vessel deployment across the Atlantic Ocean. The physical return of a spacecraft was not a secondary logistical concern. It was a primary survival problem that could only be solved through maritime coordination. During the missions of Freedom 7 in May 1961 and Mercury Atlas 9 in May 1963, vessels like the destroyer USS Abbott deployed specialized teams to secure the spacecraft. Navy frogmen jumped from helicopters to attach flotation collars, stabilizing the capsules in open swells. This phase required precise timing and mechanical coordination to manage water, impact shock, structural flotation, and safe hoisting onto carrier decks. The engineering requirements of capsule recovery directly mirrored the design constraints of marine vessels. The spacecraft had to act as a seaworthy boat while protecting the occupant from the immediate force of water impact. Designers utilized a water impact shock absorber and a pressurized hull capable of maintaining structural integrity against ocean waves. These operations turned theoretical physics into a standardized procedure, demonstrating that the space program's final orbital phase relied on maritime engineering. Once these recovery procedures proved reliable, the operational bridge between sea and space was complete. With the physical logistics of spacecraft retrieval resolved, the focus of federal policy shifted. This success prompted a reassessment of national goals, directing public capital away from the oceans and toward the moon. In May 1961, President John F. Kennedy committed the United States to landing a man on the moon before the decade was out. This single geopolitical directive transformed NASA's administrative structure, initiating a massive fiscal realignment that prioritized lunar exploration. The agency's total budget expanded rapidly, rising from $485 million in fiscal year 1960 to $1.825 billion in 1961, and climbing to over $5.1 billion by 1963. As congressional appropriators poured capital into lunar hardware. The broad-spectrum research model of NASA's early years faced sharp contraction. Congressional committees increasingly questioned the allocation of resources to non-space projects. Under this scrutiny, the Office of Advanced Research and Technology, which had managed subaquatic research and high-pressure materials testing, saw its developmental focus narrow. Inside the agency's ledger sheets, the modest funding for ocean-related investigations, which had hovered around $3 to $4 million in 1960, was cut by 30% to just $2 million by 1962. This institutional shift was completed in March 1963, when NASA Administrator James E. Webb issued an internal memorandum ordering that ocean research facilities, data analysis personnel, and sea launch tracking assets be reassigned directly to the newly established Apollo office. This transfer was accompanied by a broader reorganization where the majority of the Office of Advanced Research and Technology's resources were systematically reassigned to the Apollo program. This consolidation was administrative, fiscal, and institutional all at once. The decision reflected a practical redirection of existing assets to support spacecraft telemetry and crew recovery logistics, preserving the proven engineering value of ocean systems under a new operational banner. By fiscal year 1965, as Apollo spending reached 70% of NASA's discretionary budget, the dedicated oceanographic research lines disappeared entirely from the agency's budget submissions. Proven subaquatic capabilities were subsumed by the strategic demands of the moon race. This migration of federal capital effectively closed NASA's initial chapter of direct marine exploration, redirecting the nation's scientific infrastructure entirely toward outer space. The physical footprint of NASA's subaquatic research collapsed as the federal budget redirected toward the lunar landing. In the early 1960s, the agency established a leased field station on Bimini Island in the Bahamas to study wave dynamics and sea surface temperatures. These Caribbean experiments provided empirical baselines for early satellite telemetry and spacecraft splashdown logistics. By 1965, the funding that sustained these island operations was transferred directly to the Apollo program. NASA chose not to renew the Bimini lease when it expired in 1967, returning the property to the Bahamian government and transitioning its tasks to standard satellite tracking. A similar contraction occurred on San Clemente Island, California. Since the late 1950s, NASA's Office of Advanced Research and Technology had used the island's hydroacoustic arrays and deep water test tanks to study underwater sound propagation. In 1965, the Office of Naval Research issued a formal decommissioning order for the San Clemente site. NASA dismantled its testing tanks, packed up its monitoring gear, and returned the facility to exclusive Navy control. These closures were part of a broader institutional division. Office of Advanced Research and Technology minutes from June 1964 record a formal request from the Navy to reclaim key shared acoustics ranges for classified anti-submarine work. NASA contested the reclamation but ultimately yielded exclusive rights, retaining only limited time slots for telemetry tests. By 1970, NASA's direct undersea presence had vanished, replaced by orbital remote sensing platforms like the Tyros weather satellites. But the rapid closure of these physical installations left a final gap in the historical record. Deep within the declassified naval acoustic logs generated during these joint operations, researchers found a series of unexplained telemetry events, unattributed signals captured in the deep ocean that remained unresolved long after the facilities themselves had been dismantled. The archival record of this joint era contains a series of unresolved anomalies preserved in declassified naval logs. Between 1962 and 1968, hydrophone networks at the Atlantic Undersea Test and Evaluation Center, or IUTEC, recorded multiple unattributed acoustic traces. According to the NASA Technical Report Server Hydrophone Survey, these events occurred near 24 degrees 42 minutes 20 seconds north and 77 degrees 46 minutes 9 seconds west. The logs describe signals concentrated in the low frequency bands between 1 kHz and 5 kHz. Rather than suggesting mythic origins, the official logs treat these entries strictly as anomalous physical data requiring mathematical analysis. Operators noted them as unexplained telemetry events, unidentified acoustic signatures that disrupted standard tracking and communication channels. These naval records show that the primary effort was to isolate and filter these signals out of the background noise of the ocean. To do this, engineers had to develop advanced signal processing and pattern recognition algorithms. These noise reduction tools, designed to clean up underwater data streams, found direct utility elsewhere. The mathematical models developed to study these specific oceanic anomalies were subsequently shared with NASA, where engineers adapted them to filter out ionospheric interference and noise in spacecraft telemetry downlinks. In the academic pursuit of signal clarity, the unexplained sounds of the ocean depths directly informed the algorithms used to receive the first clear data streams from outer space. Handling ambiguous marine signals established a lasting methodology for managing data uncertainty. Because the source of these low-frequency acoustic traces remained unidentified, engineers could not rely on conventional tracking models. Instead, they treated the unresolved data as a strict mathematical problem. This ambiguity forced researchers to refine matched filter algorithms designed specifically to isolate faint signals beneath layers of dense background noise. These noise reduction methodologies helped establish uncertainty as a valid scientific category, prompting developers to analyze acoustic properties to improve signal correlation and noise separation. The details of this technical transfer are preserved in NASA Technical Report 1965 TR12. The document outlines how these matched filter algorithms, originally built to decipher sonar patterns in the ocean, were adapted to decode high-rate telemetry streams. By treating unknown parameters as problems of statistical probability, engineers established rigorous interpretation standards. These mathematical frameworks allowed receivers to identify weak signals against cosmic noise, directly reducing bit error rates during deep space missions. In 1967, the Journal of Spacecraft and Rockets, Volume 4, detailed how these sonar-derived filters became essential for maintaining reliable communications during lunar orbits. The legacy of these joint undersea investigations was the creation of an ultra-disciplined engineering methodology. By keeping the abyssal record open, yet bounded by strict analytical limits, early space researchers turned unresolved oceanic noise into a baseline for mathematical precision. The declassified files remain in the archives, preserving a historical record of engineering caution. Today, our gaze remains fixed on distant worlds, even as the deep ocean that forged our path to the stars remains largely uncharted. Declassified naval telemetry reminds us that the abyss holds unsolved anomalies of its own. As we prepare to return to the moon, we must ask if we ignored our most vital frontier. Share your thoughts below.